Similar to half wave rectifier, we can also make a full wave rectifier which takes the advantage of diodes connected in a mesh. You can see over here on the left hand side, or you can also call this as an edge bridge configuration. Edge bridge configuration. And we can use this configuration to obtain full wave rectification when we want to convert input signal of AC voltage into DC voltage. So in this circuit, we have actually 4 diodes. In half wave rectifier, which we saw in the previous video, it had only 1 diode. But now we have 4 diodes connected in an edge bridge configuration, and then there is a resistor R, and we have input voltage terminals. So we will see how this circuit operates, convert our AC into DC voltage. And once again, we have AC input over here, which is sinusoidal, and we will assume Vm is equal to 1 if needed for the numerical problem. It's a sinusoidal input from 0 to t, which is a time period, and then we have t by 2. It's half time period, and then we have half time period for the next half of the cycle. So the reason behind dividing this time period into 2 is that we have 2 phases of this input. So you can say one is positive phase, and then another one is negative phase. Or you can say negative cycle. In some books, they use this word of positive cycle and negative cycle. So don't get confused with that. So now let's see what happens when we apply an input AC voltage to this terminal and how these diodes operate. So for the first half of the input signal, which is positive, so we will have this positive terminal over here and this negative terminal over here of the input AC voltage source. So the reason behind taking consideration of this positive and negative terminal is that diodes, they operate in forward bias condition when positive terminal is connected with the positive terminal of the source. So if this is negative and this is positive terminal of the AC source, then this will be in reverse bias condition. So for forward bias, we will assume that our circuit is short circuit and it is on. And for reverse bias condition, we will assume that diodes are off, which is actually open circuit. Okay, so when the voltage is applied to this edge bridge configuration of diodes, we have this positive terminal, we have this negative terminal. So these nodes become positive and these become negative. So at this point, if we look at this first diode, let's talk about first diode. So this is in reverse bias configuration because this is the negative terminal of the diode, this is the positive terminal of diode. And we can clearly see that positive terminal is connected with the negative terminal. So in this situation, the first diode will be off. But if we look at the second diode, this is the positive terminal, this is the negative terminal, and we can clearly see that the positive terminal is connected with the positive terminal of the diode. Hence, this will be in forward bias condition, and we will have a flow of current arriving at this point, which will pass through the resistor in this direction. Okay, let's call this a current I. What happens with the D3 and D4 diode? So let's, there is a typing mistake, so please take notes of this. This is D4. Okay, this is a typing mistake. So now for these diodes, what happens is that this is the negative terminal for the first phase, right? For 0 to T by 2. For this phase, we are talking about this phase. So this terminal will still be negative, right? And if we look at D3, these are the configurations or pins or terminals of this diode. So this is positive, this is negative. Now we can clearly see this negative terminal is connected with the negative terminal. So when same terminals are connected, we call that diode in forward bias condition. So this D3 will be in forward bias condition, which means this will be on. Now, if we look at this D4, which is the fourth diode, its pins are in this configuration positive, negative. Now, at this input signal, this is the negative terminal, right? We are still talking about the first half of the signal. So this is negative terminal connected with the positive terminal. So this D4 will be in, let me write it as like RB, which is reverse bias condition, hence it will be off. So this diode and this diode will be open circuit. Let me change the color of pen to black. So this D1 and this D4, they will be open circuit. We will only have flow through D2 and D3. So if I make this diagram, so this will be like this. We have this terminal, right? This will be open circuit, right? This is the open circuit part, and this goes straight. Let me redraw it. Sorry, I just made a mistake. So let me redraw it. This will be open circuit. Okay, the first diode is open circuit, but the second diode, we already saw this. It is in on condition. So this will be short circuit. Okay, we are assuming ideal conditions for diode, so it will have no voltage drop. Then we have this terminal, we have resistor over here. This is connected like this, minus plus, this is V0. Now coming to this point, this will once again be short circuit, right? And this diode 4 will be open circuit. And then we have this signal or this connection, negative, positive. So if you look over here for the diode number 1 and diode number 4, they are open circuits, right? They are open circuit. So we will have a flow of current coming like this, passes through D2, then it will passes through the resistor, right? It will go on and it will passes through D3 and arrive at this negative terminal. So actually this becomes a series circuit. If you look at this way, this is the top terminal, right? Then we have this diode, which is D2, right? Then we have resistor, it goes to this part. Then we have this resistor, which is this diode, which is D3, right? And then we have this negative terminal. So this is actually a series circuit, right? So current will flow in positive direction from this resistor. So what will happen is that we will get an output. This is the input graph. So the output will be same as this one, right? This is for the half of the time period. Now what happens is that when the input signal enters this negative part, so the polarities will change. This minus will become plus, this plus will become minus. So let's see that in the next slide. So you can So you can see over here that the polarities has reversed. Previously it was positive, now it is negative, and the bottom terminal, that is positive now. So what happens in this situation is that this is positive, right? So this sign will appear over here. This is negative, so this will be over here. Now we simply have to check the configurations of diode, whether it is in forward bias or reverse bias. So this is negative, this is negative, this is positive, this is positive, this is negative for these diodes, right? So negative sign is connected with negative sign. So D1 will be on. Negative sign is connected with positive sign. So this D2 will be off. Now coming to this point, this is plus. We can see this configuration is positive, this is negative, this is negative, this is positive. So this plus is connected with this plus, right? So this diode will be in forward bias condition and this D3 will be in reverse bias condition, which means it will not operate, right? So now we will have a flow of current in this direction, like it will flow from here like this, it goes there, then move towards this resistor, then goes here and goes outwards toward this negative sign. So once again, this is a this is a series circuit. If I draw it this way, we have this diode over here, which is in short circuit. Then we have resistor over here, right? We reach this point. Then we have a short circuit diode over here, and then it goes towards this negative. This is negative sign, and this is positive sign. This sketch is a bit messy, but if you look at it, this is a series circuit, right? So this is series circuit. It will have same flow of current, but the key point is that this is positive, this is negative terminal, right? So the flow of current in this resistor is still same. Previously, we saw the flow of current in this resistor was from right to left. If I draw it over here, this is plus, this is minus. For the first half cycle, the flow of current was in this direction. It's still the same. You can see the flow of current is in this direction, right? So once again, we will have an output like this. So although our input was in negative half cycle, but we saw our output is in positive half cycle. So this is the theory behind the full wave rectifier, and we get this advantage that the half signal is not lost. In half wave rectifier, we saw this signal was lost, and due to which the power was almost 50%. But for this scenario, this signal is not lost, and we get full wave rectification. Now, how to solve this mathematically? We will follow the same steps we did in the half wave rectifier. Let's see that in the next slide. So in order to find the DC voltage for full wave rectifier, we got this half cycle for the positive part, and then we have this half cycle once again for the negative cycle, right? This was the input, but we got this flipped negative cycle to the positive cycle. What we are going to do is that we are going to find the area. Now, we can find area from 0 to t, but the issue is we cannot do this in single step, because our sine wave function is actually negative from t by 2 to t. So we cannot directly write this like from 0 to t sine omega t. This is not true, because after t by 2, this signal is actually negative of sine omega t. If we want to solve it in one step, what we can do is that area is equal to from 0 to t by 2 sine omega t plus then from t by 2 to t. Now this is sine omega t. So it is flipped. So what we are going to do is we are going to add negative sign to it. Okay, just take notes of this. You cannot directly do this. This is incorrect. You cannot directly integrate from 0 to t. I will tell you another easy method or easy solution. We already calculated area for this half wave rectifier sine omega t, and this was 2 by omega, and we calculated its DC voltage as 1 by pi. So this is the same signal as the previous one, right? So it doesn't change. So what we can do is that we can simply multiply this area with 2 to obtain the area of this full time period, right? This is 1 times, and then this is 2 times. This is the same path, but just move from t by 2 to t. So I can simply multiply this area with 2 to obtain the area from 0 to t. And then what we are going to do is that once we obtain that area, we will multiply it with 2. So this will become 4 by omega. But instead of going into that, what we can do is that we can directly multiply the DC voltage of half wave, which was 1 by pi, and we can multiply it with 2 to get DC voltage of full wave. So this would be 2 by pi. So this is the theory and mathematics involved in the full wave rectifier. Okay, and there is this note: idle diodes are considered. Yes, remember that. Once again, we are assuming idle diodes in this half wave and full wave rectification, because normally what happens is that in diodes we have this voltage drop of 0.7 volts. But here we have been talking about short circuits. So if we talk about short circuit, that means in that situation, the voltage drop is 0 volts. So that's why whatever we give input to the circuit, we got that at the output. So this was about full wave rectifier. In the next example, we will talk about Zener diodes, how we can use that to our advantage. Because the application of Zener diodes is that it is used for protection of our circuits and appliances, equipments, and all the circuits, electrical circuits, because it limits the voltage. And we will solve this problem numerically to see how it actually does that.